We've been talking about the hydrolysis of salts in water. Now, what hydrolysis means is that after a salt will dissolve in water, that you have to worry about the ions of that salt re-reacting with water. And we know that water is amphoteric, in other words, that it can react as both an acid and a base. So inside of the solution, there are plenty of H+ ions and also OH1- ions available for these new positive and negative ions to potentially create a new chemical with. So yes, we have to consider this as a possible source of changing the pH of our solution. Now, generically, this is called solvolysis. Lysis simply meaning the splitting apart of, and then solvo is specific to a solvent. Hydrolysis is the splitting apart of water and therefore the reacting with water. Now, from the previous video, we did watch and see that if your anion reacts with water and combines with the hydrogen from water, if it forms a strong acid, that reaction will not occur. However, if that anion does react with the hydrogen and create a weak acid, which we know since there's only 7 strong acids, there's a lot of weak acids out there, that reaction will in fact occur and set up its own equilibrium. So theoretically speaking, there are a lot of salts out there that will change the pH of a solution. The same is going to be true with our bases. Bases, if there's a component inside of the salt, once it's dissolved, if it re-reacts to form a weak base as a product, that will change the pH of your solution. So let's see what this looks like in practice. Let's look at a familiar example here. We have KCl. If KCl reacts or dissolves in water, it's going to form potassium and chloride ions. If the potassium ion re-reacts with water, it would form potassium hydroxide, a strong base. Since that is aqueous and it will dissociate again to 100%, that reaction does not occur. The same is true for the chloride ion. If the chloride ion re-reacts and hydrolyzes with water, it will pull off a hydrogen from water, forming HCl. HCl, being a strong acid, dissociates to 100% and therefore does not form. So neither component of KCl will serve to change the pH of the solution. Second example, sodium hypochlorite. When that first dissolves in water, it will dissociate into its 2 constituent ions, hypochlorite and sodium. And let's take a look at each one individually. I don't really think that we have to worry about the sodium ion, but the hypochlorite is kind of an interesting case. The hypochlorite, if it does react, will want to neutralize that -1 charge. So it's going to pull a proton away from the water, forming hypochlorous acid and hydroxide ion. Because hypochlorous acid is a weak acid, it cannot fully dissociate again, and therefore does form and creates its own equilibrium. In the process, it's going to leave behind a lot of hydroxide ion and actually change the pH of the solution. It'll actually test basic. We can write a equilibrium constant equation for this, an equilibrium expression. And you can see that that's denoted by the hypochlorous acid times the hydroxide divided by hypochlorite. Now, what's kind of interesting, we take this Kb expression that we just wrote. I just kind of want to show you how this is all related to what we've done before. I'm going to multiply that times the value of essentially 1. Hydrogen ion divided by hydrogen ion. Now I want to rearrange this equation just a little bit for convenience. So what I'm going to do is I'm going to shove the hydroxide ion from the numerator over, and then the hydrogen ion from the denominator to the left-hand side. And it kind of rearranges things a little bit conveniently. Now what that means is that I would be looking at hypochlorous acid divided by hypochlorite times hydrogen ion, and that's essentially the inverse of Ka of hypochlorous acid. And I'm multiplying that times hydrogen ion times hydroxide ion. Well, that's Kw. So essentially what I'm saying then is that Kb for this salt ion equals Kw divided by the Ka of hypochlorous acid. So now we have a very quick and convenient way of calculating an equilibrium constant for any salt. Because what you should notice is that if I needed to do an equilibrium problem with the hydrolysis of hypochlorite, the ion, look at any Ka or Kb chart that you'd like. You're not going to find a K value for it. That's something that we're going to need to generate before even beginning the equilibrium problem. And of course, we can simplify the term down at the bottom of the screen to Ka times Kb equals Kw. Let's see what this looks like in action. So here's our problem. Let's calculate the pH of a 10th molar solution of sodium hypochlorite. And of course, I'd first like to set up the hydrolysis equation at the top of the screen with the hypochlorite reacting with water to form hypochlorous acid and hydroxide. Again, that hypochlorite wants to neutralize that -1 charge and takes a proton away from the water. First step, I need an equilibrium constant. There is no published equilibrium constant for hypochlorite, so I need to produce one. The only K value that I can find is the Ka for hypochlorous acid. And unfortunately, in this equation, this is acting as a base. Notice that's forming hydroxide, so I really need a Kb. Luckily, the two are related. So Ka for the hypochlorous acid is 3 times 10 to the negative 8. And I know through the equation Ka times Kb equals Kw. So I plug and chug what I know, and I find that the Kb for hypochlorite is 3.37 times 10 to the negative 7th. Now I'm ready to start plugging and chugging, just like we would for any other equilibrium problem. There's just a tiny little extra setup with a salt hydrolysis problem. So we have our Kb value, and we do know our initial concentrations, 10th molar for the hypochlorite, 0 and 0 for the two ions at the end. Now, since we know our Kb value, we can assume that the change is going to be defined as x. And luckily, since it's 10 to the negative 7th, we can ignore the change to the initial concentration. So layer in our changes, and then we can describe our equilibrium concentrations. Now we're off to finish our equilibrium problem. So I fill in, making x squared divided by 0.1 equals 3.3 times 10 to the negative 7th, and solve for x. And I found that x equals 1.8 times 10 to the negative 4th. And now it's simply a matter of plugging and chugging into some pH equations. So what that means is that my hydroxide ion concentration, again, is 1.8 times 10 to the negative 4th. And if I negative log that, I find the pOH at 3.7. Subtract that value from 14 to get the final pH at 10.3. Now that's lovely. It was kind of a standard problem for working with an anion, but I also want to show you an example of working with the cation from a base, hydrolyzing with water. So let's take a look at the example of working with a 10th molar ammonium chloride solution. Now, ammonium chloride is a salt. It's neither acid nor base, because it doesn't start with hydrogen, it doesn't end with hydroxide. We know that because it's aqueous, it's going to immediately dissociate once it gets into the water and form ammonium ion and chloride ion. Now I have two hydrolysis equations that are possible, and I wrote those two on the screen for you. The chlorine, wanting to neutralize its -1 charge, may decide to take away a hydrogen from the water, forming hydrochloric acid and hydroxide. Now we know that that's not going to happen. Hydrochloric acid, because it's a strong acid, completely falls back apart again, and it doesn't allow for that reaction to occur. However, the ammonium ion with its +1 charge would really like to donate a proton to the water, forming ammonium and hydronium ion. Now we know ammonia to be a weak base, so this in fact is a hydrolysis equation that does work. Notice the double arrow, it does form an equilibrium, and that's what we would need to use to actually calculate the pH of this solution. And so now we can start our problem. So we'll start our world according to Donovan problem with my dissociation of my NH4+. We already know the initial concentrations. The only issue is I don't have a K value for this yet. Since we're forming hydronium ion, we know that this is acting in an acidic fashion, so I need a Ka. But all I have is a Kb value for NH3. We'll need to convert it. So my Kb value for H3 is 1.8 times 10 to the negative fifth. I plug that into the equation, Ka times Kb equals Kw, and I find that my Ka value for ammonium is 5.6 times 10 to the negative 10th. So now I'm finally ready to start my equilibrium problem. Now, since we have the K value, of course, we're going to mark the change as X, and because it's to the negative 10th, there will be no change to the initial concentration of 10th molar. So we can go ahead and define our changes and our equilibrium concentrations. Now we set up our equilibrium problem. X squared divided by 0.10, products divided by reactants equals Ka. Plug and chug, and we find that our X value is 7.5 times 10 to the negative 6th. Now that's our concentration of hydronium. So we're hopping a skip away from calculating the pH. Since pH is the negative log of that hydronium ion concentration, all you have to do is plug and chug it into the calculator, and you find that the final pH is 5.1. So that's how we're going to calculate the pH of a salt solution. Again, the first and most important thing to realize is how is it going to dissociate, and do either one of those ions react with water to form either a weak acid or a weak base. It's those particles that end up changing the pH of your solution.